Hey guys, welcome back. We are taking a look at 6-2, day one of this. We're going to spend a couple days on this. Today we're going to look at more of these radical expressions, but we're going to look at how to multiply them. The next lesson will be, you guessed it, dividing these things. All right, but let's focus just on multiplying these things right now. How do we multiply with radical expressions? Um, so, um, to multiply or combine radical expressions, especially if we have products. All right, let's forget about that word if. All right, what we're looking at here is if I have the nth root of a times the nth root of b, then that is the nth root of a times b. All right. So in other words, if the indices or the indexes, indices is just a plural of the word index, if the indices are the same, I can multiply the two radicands. All right. Now, if these indices aren't the same, we're going to see that here in just a little bit, then I really can't do much with it. All right. So let's just get into some examples here. So if I want to multiply the cube root of 6 and the square root of 2, I can't, all right, because this is a cube root, and this is, even though there's nothing there, that index is 2, that's a square root. I can't do anything with that, all right? So if the indices aren't the same, we can't do anything with it. Here, I've got the cube root of -4 and the cube root of 2. All right, well, here the indices are the same. All right, so that means I can go ahead and multiply these, and it'll be the cube root of -4 times 2. Again, if the indices are the same, I can simply go ahead and multiply the two radicands. And now it's just order of operations, so I do what's under the grouping symbol there. So -4 times 2 is -8. And then I look and see if I can simplify it from there. The cube root of -8 is -2. All right, -2 times -2 times -2. You can do that on your calculator, or again, hopefully you'll get to know these well enough that you can do these without a calculator. Okay. All right, and again, these are other examples you can look at if you want. If you have questions on those, let me know. But we're going to go on from there. Okay, so if the indices are the same, we can multiply the radicands. All right, that's not too bad so far. All right, now I want to look at how do I simplify. What does it mean to simplify a radical expression? Okay. Um, and a radical expression is in simplest form if the radicand, and again, remember that radicand is the number underneath the radical symbol. If the radicand has no perfect n factors. Okay, and I'll talk about what I mean here in just a little bit. Okay, as I go through this. So again, if I'm talking a square root, and we're going to look at a square root, we're going to look at a couple cube roots here. All right, if the radicand, a radical expression is said to be in simplest form if that radicand has no perfect n factors. Now, what do I mean by n? Well, in this case, all right, in this case, n is 2. N is referring to your index. Okay, so we are looking here. The radicand, does 24 have any perfect square factors? All right, are there any factors of 24 that are perfect squares? All right, now again, 24 has a lot of factors. 8 and 3 are factors of 24, but neither one of those are perfect squares. 12 and 2 are factors of 24, but neither one of those are perfect squares. But 4 is. 4 is a factor of 24, and it's also a perfect square. All right. So what I can do is I can write that as the square root of 4 times 6. So what I want you to catch here is that since this radicand, since 24 has a perfect square factor, this thing is not in simplest form. All right, so I'd like to put it in simplest form. All right, and here's how I'm doing this. So I can write 24 as 4 times 6. And now I'm going to go back to this. All right, we did it this way, right? We did it if I'm multiplying two different radical expressions, I can multiply the radicands. Well, now we're going to look at it going opposite. All right, this equal sign is a two-way street. It goes either way. So now here, A is 4 and B is 6 in our example. So what this says is if you're multiplying something underneath a radical, you can break it apart into two different radical expressions. Here's what I mean by that. And again, I'm not going to put the little square symbol there anymore, but the square root of 4 times 6 I can write as the square root of 4 times the square root of 6. Okay, so again, we're going that two-way street. We're going the other way. And now the square root of 4, I know what that is. That's 2. Square root of 6, I don't know what that is, so I'm just going to leave that the square root of 6. Okay, and now this is in simplest form because the radicand, 6, has no perfect square factors. The only factors of 6 are besides 1, all right? And we really don't count 1 because dividing that by 1 doesn't change it. So let me other than 1. I probably should put that up there, all right? Because 1 is going to be a perfect fifth factor, a perfect fifth root, a perfect fourth root. So other than 1. So 6, if I look at the factors of 6 other than 1, 2 is not a perfect square. There's not a perfect square. 3, 6, all of the factors of 6, or none of the factors of 6 are perfect square factors. All right. So these two are identical. The square root of 24 and 2 times the square root of 6 have equal values, but this is said to be in simplest form. Okay, and I can tell that you guys don't believe me, so let me just show you real quick. If I do the square root of 24, first of all, let me just note here that it hurts that you guys don't believe me. That I don't know. I thought we had a better relationship than that. But square root of 24 is that big irrational number, and if I do 2, now I don't need to hit my times symbol. If I just do 2 and then type in square root of 6, my calculator knows that I want it to multiply. I get the same exact number. So 2 radical 6 and the square root of 24 are identical, but this is in simplest form. This is not. It's kind of like saying 3/6 and 1/2 are identical fractions. One is in simplest form and one is not. Okay. So we've done the square root of 24. Let's look at the cube root of 24. All right. So now, does 24 have any factors that are perfect cubes? All right. Now, it'd be great if we were in my classroom and I have all those posters up there. But let's look at some of the perfect cubes again, other than 1. So 2 cubed, 2 times 2 times 2, that's 8. Oh, wait a minute. 8 is a factor of 20. Is a factor of 24. So again, just like I did over here, I can break this apart into the cube root of 8 times 3. Now, why did I do 8 times 3 and not 6 times 4? Because neither 6 or 4 is a perfect cube. I'm looking for perfect cubes now instead of perfect squares. Now, again, I can rip this apart. So that's the cube root of 8 times the cube root of 3. And the cube root of 8, well, you can see it over here, is 2. So this would be 2 times the cube root of 3. Again, those are identical expressions, but this is in simplest form. This is not. And again, you wouldn't necessarily need the multiplication symbol there. Just like with variables, I could also write that 2 cube root of 3. I could write that way as well, but I'm putting that multiplication symbol in there for you. Okay. So now let's look here. What if we throw some variables in here? Well, the first thing I'm going to do is I'm going to rip this up into, I like to rip this up into numbers and variables. So I'm going to look at it as the cube root of 54 and the cube root of x to the 5th. All right. I'm going to deal with my numbers and I'm going to deal with my variables kind of separately here. So cube root of 54, does 54 have any factors that are perfect cubes? Well, 8 is not a factor of 54. Let's go to the next perfect cube. 3 cubed, 3 times 3 times 3 is 27, and 27 is a factor of 54. All right, so I can break this up into the cube root of 27 times the cube root of 2. Or cube root of 27 is 3 cube root of 2. So I've simplified the cube root of 54. Now, what about the cube root of x to the 5th? Right? What is a perfect cube that is also a factor of x to the 5th? Well, if we catch here, x to the 5th, remember when I multiply things with like bases, I can add the exponents together. So x to the 5th I can write as x cubed times x squared. All right? So let me do that. So that would be the cube root of x cubed times the cube root of x squared. And the cube root of x cubed, is just x. And the cube root of x squared, I don't know what that is, so I just leave it the cube root of x squared. And now this is an okay answer, but again, this is all multiplication. All right, so since it's all multiplication, let me move that multiplication symbol over here just a little bit. Ignore that one. All right, since this is all multiplication, I can multiply into whatever order I want. I'm going to multiply the stuff that's outside of the radicals, so 3x, and then I'm going to multiply these two, and I am going to go ahead and write them underneath one radical. So we've simplified that radical expression. Now that one was a little bit tricky. So let's look at just one more here. So the cube root of 128. All right, 128x to the 7th. So again, I'm going to write that as the cube root of 100. Excuse me, cube root of 128 and the cube root of x to the 7th. Now let's see, factors of 128 that are perfect cubes. Let's see, will 8 go into 128? Yes, it will. Okay. Now let's hold on to that. Because I want to get the biggest perfect cube I can. Just like putting a fraction in simplest form. If I ask you to put 12/24 in simplest form, you could divide by 2 and get 6/12, and then divide both of them by 2 again and get 3/6, and then you could divide by 2 again and get 1/2. All right, you got there. But if you can recognize, hey, wait a minute, let me divide both those by 12. If you can find that biggest number that divides both of those, it just gets the job done a little bit easier. So while 8 is a factor of 128, I just want to see if there's a bigger one that works. 27 does not work. Okay, let's check just real quick. Let's check 4 cubed. 4 cubed is 4 times 4 times 4. That's 64. Oh, I think that's it because that's 64 times 2. All right, so I can do that. That's the cube root of 64 times the cube root of 2. So the cube root of 64 is 4. So this is 4 times the cube root of 2. Okay, now similar thing here. The cube root of x to the 7th. Now again, just like I did here, okay, I could write x to the 7th as x cubed times x to the 4th. Now, why am I doing x cubed? Because we're talking about a cube root, and I know the cube root of x cubed is just x. But is that the biggest perfect cube? Well, now we think about, factors, or I'm sorry, multiples of 3, all right, or another way I can write this, I could also write this as x to the 6th times x, or x to the 1st. And this is also a perfect cube. Okay, this is x squared times x squared times x squared. So this is the biggest one that I can write it as. So x to the 7th, I'm going to write as the cube root of x to the 6th times the cube root of x. And we talked about these in your last notes. The cube root of x to the 6th, all you got to do is divide these two things. So that's x squared. And that's why another reason I went with x squared, x to the 6th. I want to find the biggest number, okay, that is divisible by 3. And now the cube root of x, I can't do anything with that. And so now I do some multiplying here. I do some commutative property. So I do 4 times x squared. That's 4x squared. And then I'm going to multiply these, and I can do that because they both have the same index. And it's the cube root of 2x. So we've simplified that radical expression. All right, so simplifying radical expressions. Finding those factors that are perfect squares or perfect cubes or perfect fourth powers. Okay, and so now just one more problem here. Okay, so this is kind of a combination then. We're going to multiply, and then we're going to simplify. All right, so if I look at this, now again, I can multiply because they're both square roots. All right, so I'm going to multiply, and I'm going to put them underneath one big square root, and I'm going to multiply whatever I can. So I can multiply 72 by 10. That's 720. I can multiply x cubed times x to the 1st by adding the exponents. That's x to the 4th. And then I can multiply y squared times y to the 3rd by adding the exponents, and that's y to the 5th. So here's what I get when I multiply, but now I want to simplify that. So again, I'm going to break it up. The square root of 720, the square root of x to the 4th, and the square root of y to the 5th. So square root of 720. Let's see if we can find some factors of this that are perfect squares. All right. So let's see what we can do. And again, oh, this would be so great if I was in my room and we had those posters up there and we start going through the perfect squares. Because I know I'm gonna have to grab my calculator. Because again, 4 might work. 9 I can see works, but I want to find the biggest one. All right. So let's just start looking here. So let's see. 720. What's a if I check? Oh, let's check. 160. Let's check 144. That's 12 times 12. Whoops. 720 divided by 144. No, shoot, but that's kind of pretty. Let's see if I do 70. Let's do that was 72. How about if I do 720? Let me try that divided by 144. Oh man, that was a lucky guess on my part. All right, so 720 divided by 144 is 5. So I can write that as 144 times 5, or 12 times the square root of 5. Here, now again, this is a square root. The square root of x to the 4th. Hey, wait a minute, I can divide those. That's just x squared. 5 divided by 2, I can't. But what's the biggest number less than 5 that is divisible by 2? Y to the 4th. I can write that as y to the 4th times y to the 5th. So that'd be the square root of y to the 4th times the square root of y. Square root of y to the 4th is y squared, and then the square root of y, I don't know, so I just leave it like that. And now I look to see what I can multiply. So here we go. I've got, these are all outside the radical, so I can multiply those. 12x squared y squared. And these are both underneath a square root. They're both perfect. They're both square roots, so I can multiply them times the square root of 5y. Phew. All right. So, take a look at this homework. All right. This would just be another similar example, but, I'll leave that to you guys. Take a look at this homework, and we're actually this is going to be the first part of the homework. I'm going to have you continue the rest of 6-1 on this same homework assignment, but this should at least get you started. Take a look there at page 371. Those problems, get those shared on Flipgrid. I'll have those answers for you. Let me know if you have any questions. Take care, guys.